Hello again, Ling 441. Today I want to wrap up our discussion of voice quality by walking you through one last measure we can use to sort of distinguish between different voice qualities in speech, and then also explain how to use that measure in our next homework assignment, which is going to be about Korean stops. So why do we care about Korean stops? Korean is actually unique in an interesting way in that it sort of uses voice quality to distinguish between particular stops. So in addition to a VOT or phonation contrast between unaspirated and aspirated stops, Korean has a series of stops which are known as fortis or maybe tense stops. And in this representation, they are transcribed with a little asterisk after the stop itself. You can get these for the affricate in Korean as well, and also the fricative S, which is kind of cool. It's because it's not, well, if like me, you're a native speaker of English, you're not going to be able to hear this distinction that easily. If you're a native speaker of Korean, you probably have it already and have no problem with this. But otherwise, it'll be different. So I'll play these examples for you first of all, and then after that, I'll explain to you what's going on phonetically or what people think is happening phonetically. So you can kind of hear, these are not the greatest recordings. When we do an exercise with these stops, you get higher quality recordings, but these are from the Sounds of the World's Languages CD database. So I'll let you listen to them. This is the unaspirated bilabial stop. Maybe I'll turn up the volume a little bit. And this is the aspirated. And even though there's noise in the background of these recordings, I think you can hear the difference between those two. And it's partly based on the aspiration right after the stop, but there's also an F0 difference, kind of like I was talking about those depressor constants last time, where voiced segments tend to lower the F0 and whatever follows them. Aspirated constants will tend to raise the F0, so you can hear that distinction. And then there's the fortis. So that's a little subtle. These are not really aspirated, but basically you can think of them as the speaker is putting more tension or effort into them somehow. And then also the velars. And I'll play, as long as I talked about them, I'll play these affricates. And the fricative. And unfortunately, that one comes through almost like a stop. But I'll just stop there and hopefully have some sense of what these sound like. And maybe you can describe them in some way acoustically. What's going on articulatorily is a variety of different things. So number one, the glottis is not open as wide during the closure of the stop as in lenis stops. So lenis stops, that's another term for these unaspirated stops here. So lenis is like weak in Latin, and fortis is strong in Latin. So that's where that comes from. So if the glottis is not open as wide during closure as it is in the unaspirated stops, then voicing will begin more quickly after the stop release in the fortis stops. You get increased airflow in the fortis stops as well, so that leads to higher F0 after the stop release. You get increased airflow for aspirated stops as well, but this is not giving you the same sort of delay in voicing as we get in aspirated stops because of this first factor, right? So basically almost zero VOT, and then also higher F0, which is an interesting combination. And then also the vocal folds, kind of because they're closer together, they're actually more tense is how they're described in the literature than in lenis stops. And the way I'm interpreting that is that you're getting greater medial compression. You're pushing the vocal folds together a little more tightly. And what we'd expect out of that is a squarer glottal waveform like what we see in tense voice EGG waveforms. Okay, so that's the basic idea, that it's mostly, like I said, a distinction in voice quality and a little bit of a distinction in phonation type as well with the fortis stops in Korean. But why do you care about this? What can we get out of this? And in order to understand it a little bit better, I want to walk us back to the very basics of acoustics, like we talked about in 341. And then we can kind of see how this gets built up on top of the sort of atoms of sound, which we normally call sine waves. So the most basic kind of sound wave you can get is a sine wave. I've mentioned this before. This one is actually kind of a cosine wave because it starts at 1, but same thing, just shifted a little bit in time. So this sounds, well, I might turn this down because, yeah, we don't need to hear this at full blast. Sounds like that. It's the most basic sound you can get. It's also kind of the most boring sound you can get. So basically what's happening is we're getting this nice smooth change in air pressure or amplitude in general over time that looks like this mathematical object called sine wave. We can define sine waves by 3 basic properties that they have, which is the frequency, how often this pattern is repeating in time, the amplitude, which is how high and low this pattern goes in the amplitude scale, and then also, or the vertical scale rather, and also phase, which is where it starts in terms of the cycle. So this one starts at 1. It could start at 0 and still have the same shape. It would just be a little bit shifted in time. That's what phase means. Anyways, this is a sine wave. This is our very basic sound. You can't get any purer than that. We also learned in 341 that you can combine more than one sine wave together to get a complex wave. So the way this works is that at any given time, you're basically adding 2 sine waves together to get a complex wave. So at any given time, each sine wave is going to have some amplitude value. This is like we look at a sample at this point in time and then figure out what its amplitude value is for sine wave 1 at time 1. We can represent this with a sub 1 of t sub 1. So sine wave 1's amplitude value at time 1. We can look at the amplitude value of sine wave 2 at the same time, t sub 1, and then all we need to do to get the amplitude value of the complex wave is to just add those 2 amplitude values together. So if this was like 0.2 and this is 0.4, the amplitude value of the complex wave would be 0.6, something like that. All you got to do to figure out what the complex wave looks like is add the values of the individual component sine waves together at every single point in time, going through the entire time scale of both waves. Once you do that, you get an interesting effect such that the sine waves, which are initially these pure atoms of sound, become what we call harmonics. So those are component sine waves of a complex wave. They're any sine wave you add together to get a complex wave. And that's just a technical term. Okay, so showed you these examples in 341 as well. It's always worthwhile to look through them again, just to remind ourselves of how this works. So we have sine wave number 1, which has relatively high amplitude. It goes to a peak amplitude of +1. The opposite of that is -1. If your highest peak amplitude is always going to be 1, the minimum amplitude is going to be -1. They have to balance out. It's also low frequency, so it's only repeating 4 times in this time scale. To that, you can add the second waveform, which is a low amplitude, high frequency sine wave. So this one only goes up to about a half on the amplitude scale and down to -0.5 maybe. And it repeats a lot more often in this time frame as well. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is repeating 12 a dozen times within whatever this time frame is. Let's say it's a second. So this one is 4 hertz, and this one would be 12 hertz if this is just a 1 second window. When you add them together, I'm not going to ask you to do the math. I'm just going to show you what it looks like. You get a pattern that looks like this, which kind of looks like a sine wave, but isn't. It's more complex than that, at least the repetition pattern, right? And it kind of has a peak amplitude of 1 that's mostly coincidental, and also basically repeats 4 times here in this time frame, but that's also kind of coincidence. The fun part of this is that you can kind of see this smaller, or this waveform 2 pattern superimposed on top of the waveform 1 pattern. So we get this big, loopy, slow repeating waveform 1, and then we get the sort of very quick repetitions of sine wave 2 superimposed on those peaks and valleys. Okay, that's just for visualization's sake. That's kind of how this works when you create a complex wave. We can look at this in another perspective, though. This is a waveform view. We can also look at it in the power spectra view. So in the waveform, we're plotting time on this axis, and I showed you this on this original this original slide as well. So we got time and pressure here. You can think of this more generally as amplitude if you want to, but that's what we're seeing in both dimensions of the waveform view. If we go back to the power spectrum view, we're going to do something different. We're going to plot frequency on the x-axis and intensity on the y-axis. So these are the kind of the two most crucial properties of sine waves that I mentioned before. So one of them is frequency, how often does the sine wave repeat in time, and the other is basically its peak amplitude, which we're going to interpret in terms of intensity on the y-axis. So instead of getting a nice view of how sound pressure changes over time like we do here, we're going to get, like this view, we're going to get a nice understanding, or a very clear understanding, of these first two properties of the sine wave. Every sine wave has the same shape, so we don't really care that much about what it looks like in the waveform view if we can know what its frequency and amplitude are. Okay, so yeah, this is what it looks like when we do actually plot these things out in a power spectrum. So this is my big loopy, slow repeating waveform. And when I plot that on a power spectrum, it just winds up being one spike. So we're simplifying things here a little bit. This is not really intensity, this is just the peak amplitude. But we're saying the peak amplitude is 1 on this y-axis, and then here is the frequency, which is 4 whatevers. If we look at the other waveform, it repeats more rapidly or more often within this time frame. So we're shifting it over here on the time scale. It's going to have a frequency 3 times as high as this one. And then its peak amplitude is only a half, right? So it doesn't go as high on the y-axis. And what's fun about this is that when we did this sort of bare bones complex wave example, we got lucky in that we were able to see the shapes of kind of both waveform 1 and waveform 2 here. That's not always the case. In fact, that's not often the case. But when we do add sine waves together and look at them in their power spectrum view, it becomes really obvious what's going on. So if I add these two together in waveform view, I get this. And if I add them together in power spectrum view, then I get the two spikes in the same power spectrum. And it's really obvious what the component frequencies and their intensities are for the harmonics involved in creating this complex wave. That's why we look at things in the power spectrum view if we want to know what a complex wave consists of or is made up out of. Okay, so, and I'll add again here that each one of these, once you put them together to get a complex wave, these are called harmonics. Okay, so I'll give you a little thought question here, and I'll pause once I get to it. But here's one little cycle snippet of my first waveform, and here's a correspondingly long snippet of my second waveform. And when I add them together, I get this complex wave. So this is, well, it's called R, but it's 1 plus 2, right? So let's say I take that complex wave cycle and I add to it another sine wave, which is even at a higher frequency and a lower amplitude than waveform number 2. So this one repeats once in this time frame, this one repeats 3 times, this one repeats 5 times in that time frame, and maybe it's at a peak amplitude like 0.25 or something. What do you think the complex wave pattern will be if I add this to this? Any guesses? I'm going to let you know that it will look like this. And again, we're getting kind of lucky in that we're seeing kind of clearly, visually, the addition of this high frequency, lower amplitude wave. We can kind of see a couple of these little bumps here at the peak and the valley of the complex wave. So this is waveform 1 plus 2 plus 3. And at this point, I want to ask you another question, which is, what if we just kept going in this fashion? So what if instead of, or in addition to these 3 that I've already added together, my next one is going to be another sine wave which has frequency of 7 hertz and has an even smaller peak amplitude. And then after that, I find a sine wave of frequency 9 hertz and it has an even smaller amplitude than the 4th one. And then I keep going and going ad nauseum or ad infinitum, however you want it. What would the waveform look like that I eventually get out of that? What do you think? When I start out, I have this one, then I go to this one, then I go to this one. If I keep going with that sort of pattern development, what would it eventually look like? You are eventually going to get something that looks like this. And this is just one cycle of it, but it's called a square wave, and it's represented by 1 plus 2 plus 3 plus blah, 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 all the way to infinity. That's plus n. And ultimately what happens is that the valley and the peak of this waveform get leveled off. So that's why it's called the square wave. Unfortunately, it kind of looks like a swastika, but let's just pretend that's not the case, because why bother even thinking about that? Okay, so the cool part is that we can kind of square this off though. We started off with just sine waves, which are curvy all the time, right? But now we've got nice sharp 90-degree angles in our waveform. That's kind of amazing. Yeah, so if I look at the power spectrum of this creature, here we're looking at multiple cycles of it, then what I'll see is that I keep adding additional sine waves to these two, which are higher in frequency and lower in amplitude. And this amplitude keeps decreasing as you go up the scale, and the frequency keeps increasing as I add each one to it. But we're going to get this nice kind of parabolic pattern. And I'll show you an example in Praat here in a second. Okay, so it's easy to see what the harmonics of this guy are, even though it'd be very hard to figure out what they are here. I will, from just a waveform representation, but I will again add something I mentioned, I think, in the first lecture, which is when you get very rapid changes in a waveform, that's a sign that you're dealing with high frequency components somewhere in the complex wave, in the spectrum composition of the wave you're putting together. So just keep that in mind. With these big loopy ones, with the sine wave, you're only getting one, so that makes it easy. But the more rapid changes you get, the more high frequency information is in the complex wave. So with that in mind, hopefully we can abstract a little bit from the specific example, but you can remember that our EGG waveforms for the different kinds of voice qualities included this one. This is for tense voice. And it's not exactly a square wave, but it looks more like a square wave than, say, our modal voice one did. Going back as well, you can think about the sort of idealized EGG waveform that I walked you guys through. That did have square tops and bottoms. This one is pretty close to it. There's a little bit of noise here, so there's some high frequency information going on. But if I'm kind of leveling off here at the bottom and the top, I'm basically getting something that looks like a square wave. And in order to do that, in order to get that sort of mathematical pattern, so to get that mathematical pattern, you need lots of high frequency components like we saw on this previous slide. You need to get these little bitty guys here at the top end in order to kind of square things off and make rapid changes in the waveform. You don't need to think about that when you're like creating tense voice, when you actually speak. Your mind or body is not, computing all the math in order to make this sort of waveform, right? You're just creating the waveform. It's the way that your vocal folds respond to certain conditions when you place a lot of, say, medial compression on them and the right amount of airflow and whatnot. So that's what we get, and what comes along with that are the harmonics that basically create the waveform, right? You're outputting something that looks like this. Because it's a complex wave, there are many harmonics in it. A modal voicing EGG looks less square. It's pointed at the top and bottom, more or less, and it's got these little angles in the middle. So again, those are some interesting. There's some interesting high frequency stuff here, and then there's lower frequency changes like these big elbows on top of the general cycle. So this is somewhere in between like a sine wave and a square wave. It kind of looks like what we call a sawtooth wave in acoustics, which is kind of fun. So that's kind of like, as usual, modal voicing is kind of in the middle. It's halfway in between all of these sort of extremes we get in voice quality. And then lastly, we can kind of briefly consider what breathy voice and falsetto voice look like. So falsetto looks like it's really sinusoidal, basically a sine wave that's repeating very quickly. Breathy voice is closer to that, sort of at this peak part. The lower part gives you some more complex information, but it's a lot closer to a sine wave than the modal voice is, and especially tense voice, right? So when we look at these guys, especially compared to like tense voice, what we're going to see in their spectrum or their spectra is a lot of intensity in the lowest harmonic, which is the fundamental frequency of the wave, and then not much intensity in the higher frequency harmonics. We're going to have sort of a dominant fundamental and less intensity higher up. With the square wave, or the tense voice wave, we should see a lot of energy in the higher harmonics, because otherwise we wouldn't be able to get this pattern. And then again, the modal voicing will be somewhere in the middle, where we have a fair amount of intensity in the fundamental, but also a fair amount of intensity in the higher harmonics too. Okay, so to kind of show you how this works, I'm gonna load up some sound waves in Praat here. So first of all, I generated a sine wave, which repeats at 100 hertz frequency. My computer speakers just got weird. So this is going to be fairly low. Frequency might not be super easy to hear in the recording. Maybe I should have made it louder, but if I zoom in, we'll see it's just a sine wave. And I'm going to take away these pulses because we don't need that information. All right, so this one starts at 0 like it should. That looks like a sine wave. So I can show you how to create a spectrum here, which you might recall from 341, or maybe you don't. Either way, the way you get it is you go to analyze, you highlight the wave, the sound file here, you go to analyze spectrum to spectrum, and normally by default this is clicked as fast, which saves on computation time for this sort of calculation, but I would recommend unchecking that, because if you do get a fast Fourier transform spectrum, you will get a sloppy spectrum, it turns out. So don't do that. Do it nice and slow and more accurately. And then this one should be very, very not exciting to look at. It's just going to show you one peak here at 100 hertz. I'm going to zoom in a little closely so that I can try to get it. Yeah. So 100 hertz, it just shows us that frequency or the top end. And it's the same sound file. Doesn't matter where I pick to play it. I can contrast that with a sawtooth wave. So we'll look at this one first of all, and I might turn this down because this will get a little bit louder. Yeah, too loud. Good thing we're not in class, and good thing I did not just damage somebody's hearing unintentionally. Maybe I did, but if you're wearing headphones while you're watching me, that's on you. Okay, so this is a sawtooth wave, and it kind of looks like that modal voicing wave we saw before a little bit, but it's got these sort of triangular patterns. So it's repeating sort of in a similar fashion as a sine wave, but obviously with a totally different pattern, right? But we can see the peaks and the valleys nice and easily. Okay, what does the spectrum look like? It looks nice and pretty, like a parabolic pattern as promised. So we have a lot of intensity in the lowest frequency harmonics. So this should be the fundamental at about, well, it's hard to click on exactly. It should be at 100 hertz. Boop, yeah, got it that time. So 100 hertz. Next one should be at 200. Next one should be at 300. They're all going to be evenly spaced apart from each other in the frequency scale. Isn't that convenient? If I play just these four, it'll sound maybe less edgy. Yeah. If I play the ones above it, you might want to turn down your volume before I play this, but it'll probably sound a little more annoying. Possibly. Yeah. Either way, what we see in terms of intensity, so the frequency is kind of set by that fundamental. They're all going to go up at 100 hertz intervals. The intensity is going to drop consistently to get us that sine or sawtooth pattern and level off there as we go up towards the high end. I also have a square wave. It's going to be hard to kind of see it here because the tops and bottoms kind of get cut off. Yeah, so it's a little bit ridiculous. So the top is like here and the bottom is there, so on and so forth. I'll play it. This will also sound annoying, so you might want to turn your volume down now if you haven't done so already. And I'll mention when I play these sounds, these were the sounds of video games when I was growing up, when they were first becoming popular, like in the early 1980s. And it's funny, once I became, a phonetician and learned about this stuff, that I finally, the secrets were revealed for how to make video games for little kids 40 years ago. You just use basic acoustics. Yeah, so like, the Wampus got you. Okay, anyways, if we want to look at the spectrum for this guy, it is going to look quite similar to what we saw for the sawtooth wave. It's got kind of an extra series of harmonics in there, though. You got to pack in a lot of different harmonics to get that sort of squared off top and bottom. Yeah, so I'm not going to go much more into this. You can see these primary harmonics are also, well, yeah. This one's at 200, this one's at 300, this one's at 400. They're still evenly spaced. But we're getting sort of this alternating pattern and intensity. We don't need to worry about that too much, except just to know that we're getting a lot of harmonics in here to get that very non-sine wavy pattern in the complex wave. Okay, so as promised, I'm going to show you some EGG waveforms that I made of myself a long time ago. This is supposed to be me doing modal voice. Maybe you can hear that. It looks a little funny because I kind of got this double peak here at the top, and I don't know exactly why. But you know, this is what we got. So we can look at the spectrum of that, and we'll focus in here on the lower frequency scale. So yeah, overall, actually, maybe I'll just play this. So there's my little buzz. That's what I'm creating at my vocal folds when I just speak like this. And you can see it's not exactly parabolic, but it's kind of parabolic, right? So we have a fair amount of intensity in the lowest harmonic, which is the fundamental frequency. So my F0 there is at 150 hertz. And then it's decreasing as I go up the scale, not, you know, consistently, but in the general vicinity of consistent. But most of the energy here is in the first harmonic. I'm actually going to load, I think, all three of these up first, and then we'll do some measurements. This is a falsetto that I produced. It says it can't even show the pitch contour because it's too high here, I guess. But you can hear that the F0 is much higher there. If we look at the spectrum, we'll be able to see that and maybe measure it too. View and edit. Yep. So here's my first harmonic. It is about 370 hertz or so, or maybe, yeah, so this one should 740, this one should be at what, 1110, 11, whatever, close enough. You can see same kind of idea, a lot of intensity in this first harmonic or the fundamental, and then it drops off as you go up the scale. Because the fundamental is so much higher than it is for modal voice, the harmonics are more widely spaced apart from each other, right? So they all got to be spaced apart from each other by the fundamental frequency of the complex wave. But overall, the intensity goes down as we go up the scale. Okay, last but not least, I got a little snippet of me doing creaky voice. And it's not great. There's a lot of noise in it. You can kind of see noise here in the waveform. These are kind of the big belches of my vocal folds as I produce creaky voice sporadically, relatively consistently, periodically for creaky voice. There's a little bump here. This stuff is noise because it was kind of a weak signal. So that's going to show up as high frequency intensity in the power spectrum. But let's take a look at that. And yeah, so this is what we get. It's a mess. But I'll zoom in here at the low end and just kind of point out that it doesn't drop off as dramatically between the first and the second harmonics as it does in the other two spectra for the EGG we produced, waveforms we produced. This is a little loosey-goosey here because it's hard to get basically a consistent sort of periodicity out of creaky voice, but my first harmonic is at 70 hertz. This one's at about 130 or so. I do want to just show you really quickly this measure that we call spectral tilt. So there's different ways to measure spectral tilt, but it's a way to kind of get at the distinction between various kinds of voice qualities, because it kind of relies on this fact that some voice qualities have more intensity allotted to the fundamental than others. So modal voice, like I said, there's different ways to measure it. The way we're going to measure it in this class is we're going to look at the intensity difference between the first harmonic, which is the fundamental frequency, but when we call it the first harmonic, we'll represent it as H1. So my H1 intensity here is about 67.5 decibels. The peak here is over here. The readout I'm getting when I'm not quite touching the peak is that. I'll try to get to the peak of the second one. This is H2, the second harmonic. It's 58. So my difference there is about 9.6 decibels, more or less. If I go over to creaky voice, zoom in a little bit. So my first harmonic is up here, 60.1 decibels. And the second harmonic is 57.8 decibels. So generally speaking, we're going to expect this measure to be kind of in the middle for modal voice as usual. For creaky voice, what we're going to expect is a low measure of spectral tilt. So spectral tilt is H1 minus H2. And for the modal voice sample, we got a H1 minus H2 measure of about 9.6 or so. For creaky voice, we're getting a measure of about 2.3 decibels or so. And last but not least, I'll go to the falsetto. And because the falsetto kind of has the most power or intensity in the fundamental, we're going to get the biggest spectral tilt measure for it. So yeah, it's about 66.2 here at the peak of this guy. The first one, and here's my second one, and that one's at 48.3. So this one's about 18 decibel difference. So we go from 18 decibel difference for falsetto to about 9.5 for modal voice to about 2.3 something for creaky voice. So the idea is the squarer your wave is, the less spectral tilt you get. Also, thinking of it articulatorily, the more medial compression you get when you produce this voice quality, the squarer your wave is going to be. So more medial compression leads to less spectral tilt in terms of this H1 minus H2 measure. Creaky's at one end of the scale, breathy or falsetto's at the other, modal's somewhere in the middle. Okay, hopefully that made sense. If it doesn't, I'll give you this spectacular graph which shows you kind of the same thing, but also kind of relates this to open quotient, and also gives you kind of a more general measure or definition of spectral tilt, which is a drop off in intensity of harmonics compared to the intensity of the fundamental. So this is nice and easy because we were able to measure spectral tilt from just EGG waveforms. We're getting kind of a more pure view, a purer view, not a more pure view of what the harmonics are doing. Normally you don't have that luxury. It's great if you can do it, but sometimes you're going to have to measure spectral tilt from just an acoustic record, like a sound recording, and you're just going to be able to look at the waveform and do a Fourier transform on that to get your power spectrum. So that can be a little bit problematic because there's more than just what's going on at your vocal folds contributing to the shape of the waveform. You also get resonance. So you can have to use a few tricks to sort of figure out what's going on there exactly. I'm kind of digressing here a little bit into things we don't need to worry about quite yet, but I'll just reiterate again that when you do get a nice clear view of what's going on with the harmonics, you can expect creaky or more tense voice qualities to have less spectral tilt. They will descend in intensity less rapidly than modal voice, and modal voice will descend in intensity as you go up the frequency scale even less rapidly than what you get for breathy or falsetto voice. And all these things are ultimately related. How open quotient, the shape of the waveform, spectral tilt, so on and so forth. They're all related to how much pressure you're pushing towards the middle of the glottis or the larynx when you're producing these voice qualities with your vocal folds. Okay, I just used a lot of creaky voice there. Hope you don't mind. Anyways, just to wrap this up and to lead to this other issue that I was kind of digressing into on the previous slide, but when we produce speech using phonation, using airflow going through our vocal folds, we get a complex wave that is emitted from the glottis, and it goes up into our vocal tract, and we can do more things with it there. But ultimately, this complex wave is going to be the source of all voiced speech sounds that we get in language. In speech, and particularly in vowels, humans can shape this spectrum to make distinctive sounds, in which case some of the harmonics that we get out of this complex wave are going to be intensified or emphasized. Others will be diminished or damped. Different spectral shapes may be formed by particular articulatory configurations. And when that happens, we call these specific intensities formants. We've talked about them a lot in 341. But the thing to remember here before we get into how formants are created is that the process of that spectral shaping requires the raw stuff of the source to work with. So for now, we're still going to stick with the source properties of speech and look at how they differ in the different series of Korean stops. It's usually a little bit easier to interpret them in terms of vowels, but that's not the only way we can use them, so we might as well kind of go all in and figure out how Korean uses them to make sort of different voice qualities for stops. And that's what our next homework exercise is going to be about. I'm going to make a separate video about that here in just a second. So I'll see you then.